Okay, welcome back. Today we're going to continue with Chapter 6. We're going to be looking at Section 6.2, which is the properties of logarithms. And in getting these properties of logarithms, we'll need to remind ourselves about lots of properties of exponents because every single logarithmic property is simply the inverse of an exponential property. To remind us of this, we're going to begin with some very basic properties relating the two together. We know that if y is equal to log base b of x, that is the same as writing b to the power of y is equal to x. Logs and exponents are inverses of each other. Because of this, they will cancel each other out. So we obtain properties where log base b of b to the x is equal to x, and b to the power of log base b of x is equal to x as well. These functions being inverses of each other, they fully cancel each other out. We talked about inverses. If I were to begin with x and then put x through a exponential function, and then put x through a logarithmic function, we will obtain the original. And it works both ways. If you start with the log and then go through an exponent, you will once again obtain the original. This will also give us a couple of ideas about some specific values of logs. Because anything to the 0 equals 1, this means that log anything of 1 will be 0. And anything to the power of 1 will equal itself, which means that log base b of b will be equal to 1. These are a couple of special points on logs, typically the ones that I like to use when graphing, just so that I can get a couple points and get a sense of how large my graph will be. Next, we'll want to look at a couple of algebraic properties. All of the exponential properties that we've seen before have a logarithmic pairing. So we're going to get three basic properties. We're going to say that b to the m times b to the n is equal to b to the m plus n. B to the m divided by b to the n is equal to b to the m minus n. And b to the m all to the n is equal to b to the m times n. Each of these properties has a logarithmic mirror. Log of m plus log of n is equal to log of m times n. And log of m minus log of n will be the log of m over n. In all of these cases, these logs can be of any base. It does not matter what the base is. And similarly, if I log any base of m to the power of n, then I can pull the n out front in multiplication. You can see how all three of these properties are similar to the exponential ones, but inverted. For example, in the first property, when I'm multiplying two different logs, then or exponents, multiplying two different exponents, when I combine them to a single exponent, it appears as addition. With logs, I am adding two different logs, and when I combine it to a single log, it appears as multiplication. It switches in terms of which one identifies when it is two separate pieces and which one identifies when it is a single piece. All of these properties can be very, very helpful when solving equations using exponents and logs. we're going to go through some basic examples of simplifying and expanding such expressions so that when we see equations with these, we're prepared to work with them. Let's start ourselves off with this, and we would like to expand and simplify. So when we say expand and simplify, we would like, instead of this being one big messy log, to write this as several distinct logarithms. Now, the first thing that we can do is we can notice that there's a lot of multiplication and division going on here. Multiplication will show up as addition, and division will show up as subtraction. So we can rewrite this log as ln of cube root of x plus ln of e squared minus ln of y minus ln of z squared. The things in the numerator are multiplied and so are added. The things in the denominator are divided and so show up as subtraction. The next thing to do is to bring the exponents out to the front. I see a 2 here, and this 1/3 root is a 1/3 exponent. We could have rewritten this entire piece as x to the 1/3. Thus, we obtain 1/3 ln of x plus 2 ln of e minus ln of y minus 2 ln of z. We've now isolated each ln so that it has only a single argument. There's one other thing we can do, which is that we know ln of e. Since ln is a base of e, this simply will cancel out to be 1. Because ln asks the question, the base to what power equals the inside? So in other words, e to what power would be e? Well, of course, e to the first power would be e. If you can't see this right away, you can do the math out on the side. Ln of e is equal to y. Let's not use y. Y is part of the problem. Let's use w again, which means that we're saying that e to the power of w is equal to e. Well, since e to the power of 1 would be equal to e, then that means that w is equal to 1, or ln of e is equal to 1. This means that our final answer will be 1/3 ln of x plus 2 minus ln of y minus 2 ln of z. Several different logarithms, but each one is itself very, very simple. It's easy to see what's going on here. Let's try it in the opposite order, taking a bunch of separated logarithms and combining them together. So this time, let's say that we want to simplify 5 log 3 of x plus 2/3 log 3 of y minus 3. So the first thing that we see that we can do is we can bring in these multiplication into exponents. So this can become log 3 of x to the 5th plus log 3 y to the 2/3. We're going to leave this 3 off to the side for last. And we will first combine these. Since they are added, we can combine it into addition. X to the 5th, y to the 2/3. Now this minus 3 cannot be combined further because it's not written as a logarithm. However, we should be able to figure out what it would need to be. We're asking ourselves the question, log base 3 of what, let's call it w again, will be equal to 3. Which, in other words, we're saying 3 to the power of 3 will need to be w, which means that I need 27 will be w. So I can rewrite this line as log base 3 of x 5th y to the 2/3 minus log base 3 of 27, which I can then simplify further since I have division as subtraction. X to the 5th, y to the 2/3 divided by 27. Now there's one more rule that we would like to look at here. The idea is the change of base formula. And the reason we like a change of base formula is this. If you have a calculator, you will notice that only the basic log and ln are on most calculators. So we would need a way to rewrite logarithms using different bases. So our starting point here is going to be log a of x multiplied by log b of a. Now, using this, we are going to use the exponential property that we mentioned to bring this first log inside as an exponent, yielding log base b of a to the power of log base a of x. And using the inverse property, this piece cancels out, leaving us simply with log base b of x. Thus, I can go ahead and rewrite log base b of a as log base, or excuse me, I want log base a of x to be log base b of x divided by log base b of a. This is the change of base formula, and we will use it when we need to take a log of one base and rewrite it in terms of log of another base. Most notably, we will want to do this when we need to use a calculator to evaluate a log. For example, if I wanted to find log base 4 of 5, the way we are going to do this is we are going to say that log base 4 of 5 is equal to ln of 5 divided by ln of 4. We could have just as easily used log base 10. It does not matter which one we pick. We just need to do one of the options that is in our standard calculator. Plugging each of these into our standard calculator, ln of 5 comes out to be 1.609, and ln of 4 comes out to be 1.386. We can divide these two. Ln of 5 divided by ln of 4 comes out to be around 1.16. All right. That's all we've got for today. See you next time.